Hi everyone, welcome back to Chem Help ASAP. Today we are going to be talking about rate laws. So we are going to be writing rate laws and defining conditions of rate laws, as well as talking about things like the order of the rate or the overall order of the reaction. Let's get started. Okay, so our task is to write the rate law for this decomposition. But we have a bit of a problem with this decomposition. Of course, initially, you only have your nitrogen dioxide, which means you will only have the forward reaction. But after a certain amount of time, your reverse reaction can also occur. This complicates things because it makes the rate of the decomposition of nitrogen dioxide dependent on the difference between the forward and reverse rates. That is going to be quite complex. We need to simplify. So what we're going to do is we're going to choose conditions that help us simplify this problem and just focus on the forward rate. So we're going to have two conditions for writing this rate law. The first condition is the concentration of the products is neglected because the reverse reaction does not contribute to the overall rate. Well, how do we make this condition true? We're going to study the initial rate of the reaction. So we're going to look at the rate of the reaction as soon as we introduce that nitrogen dioxide. So we are not going to give it time for the reverse reaction to occur. Again, this is an initial rate. Our second condition is our value of N must be determined experimentally. Now, I know you're going, where is the N? I'm not seeing the N. I will show it to you in just a second. The important thing to remember is the value of N is not determined by the balanced chemical equation. So it must be determined experimentally. So with both of these conditions held true, I can write a rate law for this reaction. And here it is. So overall, my rate, of course, is just going to be my change in concentration of my nitrogen dioxide over my change in time. Now, notice again, there's a negative here because we're talking about a change of a reactant. This part of the rate law is where N comes in. So let's talk about all of the different parts of this expression for a rate law. All right, so we first have just what our rate law is. It is an equation that defines the relationship between the reactants and the rate of the reaction. Now, this relationship is determined experimentally, so we are not writing it based on the stoichiometry. We must have experimental data. This particular type of rate law here is often called a differential rate law. You will often see differential rate law and rate law used interchangeably, but there will be another type of rate law called the integrated rate law that is different. This is why we differentiate between differential rate law and integrated rate law. Okay, so our rate law is what we have written right here. Now let's talk about our rate constant. This is a proportionality constant, and it relates the rate of the reaction to the concentration of the reactants. This is why we can put an equals here when we're saying rate equals this expression right here. So our rate constant we call K. Again, it is also determined experimentally. You cannot get this from the balanced chemical equation. It is also dependent on how the rate is defined. So in this rate law, we are defining the rate based on the concentration of nitrogen dioxide. We could also define the rate based on the change in concentration of nitrogen monoxide or oxygen. Those would have different values of K. So it's really important that you define your rate based on what you are monitoring. In this case, we're monitoring nitrogen dioxide. All right, let's talk about reaction order. Finally, this is our value of N. So you'll see our N here. It is an exponent. Just like K, it is also determined experimentally. So if you're used to writing a lot of things down just based on the stoichiometry of an equation, just know when you're talking about kinetics and rate laws, you need to determine these values experimentally. Next, I do want to talk about our overall reaction order. This is going to be the sum of the exponents in the rate law. So again, each exponent is determined experimentally. This rate law right here is simple because there is only one reactant. There is only one reaction order. It is N. So this value N is the order for nitrogen dioxide, but it is also the overall reaction order. Now, don't worry, we'll also take a look at a reaction where we have multiple reactants, and so our overall reaction order will be different from our reaction order. The main thing, again, I want to hammer home is that all of these are determined experimentally. So we can write our rate law like this, and that's totally fine, but we cannot plug in values for K or N until we have experimental data. Okay, so let's take a look at a problem that gives us experimental data. Okay, here's our problem. We're going to determine our rate law for this reaction rate here. Notice I have two reactants. So this is going to make my rate law a little more complex. But again, we can handle this. It's not a problem. So first, I'm going to write my generic rate law. Here's my generic rate law. It's just my K, which again must be determined experimentally. You can see that I have made my ozone have the order of N and my nitrogen monoxide have the order of M. Here's our table of experimental data, and you can see we have 3 different experiments. We're monitoring the concentration of ozone, we're monitoring the concentration of nitrogen monoxide, and we are given the initial reaction rate. So you remember those conditions that we talked about in the last slide? For this rate to be true, we need to look at initial rate. So we need to set this up such that we only look at the forward reaction and we don't give this reaction enough time to start having the reverse reaction occur. So this is why it's so important that these are initial reaction rates. So the first thing we're going to do is we're going to experimentally determine our value for N. So our value for N is tied to our ozone. So looking at our data for ozone, we want to choose 2 experiments to compare where ozone is changing. Okay, so we can look at either experiment 1 and experiment 2 or experiment 2 and experiment 3, right? They're changing. We don't want to look at experiment 1 to 3 because ozone stays the same. So does it matter which one we look at? Yes, it does. So we want to choose 2 experiments to look at. First, where ozone is changing, and second, where our nitrogen monoxide is not changing. So we want ozone to be changing. We want nitrogen monoxide to be held constant. That is going to be looking at experiments 1 and 2 here. So you can see my ozone is definitely changing. I'm going to put a delta there. And our nitrogen monoxide, I'm going to write constant. So these are the 2 experiments we want to use to determine our value for N for ozone. Let me show you how we set this up. We're setting up a ratio, or you can think of this as a proportionality. I am going to compare rate 2 to rate 1, and that is going to be equal to my concentration of ozone from rate 2 to my concentration of ozone from rate 1, and all of this is raised to the power of N. So this expression is not very difficult, but the hard part about these calculations is keeping everything straight. So make sure you're labeling everything clearly and that you haven't flipped things. So it's easy to set this up as rate 2 over rate 1, and then in the ozone, flip that 2 and 1. You don't want to do that. You need to make sure everything is consistent. Otherwise, you'll get some really odd numbers. Okay, so we need our data, we need our rates, and we need our concentration. I've already circled my rates for ozone. Let me circle my initial rates here. Plugging in my rate 2 first, you can see that is 22. Plugging in rate 1, that is 11. Now plugging in my concentration of ozone, again for rate 2, that is going to be 0.0020. And for rate 1 is going to be 0.0010. Let's simplify both of these. This is just simply 2 equals 2 raised to the N. You don't even need a calculator for this because, of course, N must equal 1 for this expression to be true. So a lot of these types of calculations, you can just look at this expression and you go, oh, yes, okay, I know what N equals. Bam, right there. But I will show you in a later example how to handle this expression when it's not so obvious. Okay, so that is our value of N. Our value of N equals 1. Now I need to find the value for M. So let me clear off what I've written on this table and we can look at nitrogen monoxide. So we do the same thing for nitrogen monoxide. I'm looking for experiments where nitrogen monoxide concentration is changing. So I can look at 1 to 3 or I can look at 2 to 3. But again, I also want my ozone to be staying constant. So I'm switching things up. This time I want ozone constant. I want nitrogen monoxide to be changing. Well, that is going to be comparing experiment 1 and experiment 3, because that is where my ozone is staying constant. Okay, so let me circle that on my initial rates as well. And let's write up our proportionality. All right, I'm comparing rate 3 over rate 1, which means I'm comparing the concentration of nitrogen monoxide from rate 3 to my concentration from rate 1, and this whole thing is raised to the power of M. So let's plug in my numbers. My rate 3 is 22, my rate 1 is 11, my concentration from rate 3 is 0.0002, and my concentration from rate 1 is 0.0010. Okay, so let's simplify this here. We have 2 equals 2 to the M. Again, it's the same thing. This makes it super obvious that also M equals 1. So it's okay that your order for these two reactants is the same. That's perfectly fine. So 1 is the order of ozone, and 1 is also the order of nitrogen monoxide. So if I wanted to know my overall order, I would simply add my N plus my M, which in this case is 1 plus 1. My overall order for this reaction is 2. We are not finished with this rate law yet, though. So we have determined N and M, but we have yet to determine K. Remember, K is also determined experimentally. So let's rewrite our rate law with our N and our M plugged in. So here we go. Here's our rate law. Of course, we don't put the ones in. We assume they're there. And we need to use the experimental data from any of the experiments to determine K. So let me again erase my marks. Okay, and I'm going to choose the data from experiment 1. So I am going to plug in the rate from experiment 1. I'm going to plug in my concentrations here from experiment 1, and that is going to allow me to mathematically solve for K. So here is everything plugged in. Again, my rate, my concentrations, of course, these are both just to the power of 1. And I can solve for K. So if I solve for K, I get K equals 1.1 times 10 to the 7th. At this point, I can write a complete rate law because I've determined my value of N and M, and now I have determined my value of K. So my rate law for this reaction is given right here. And you can notice instead of writing K, I put my number in. And of course, these are written with their orders of 1 assumed. Let's do one other example. Okay, we have a similar reaction here. So the first thing I'm going to do is write a generic rate law. Again, this is a differential rate law. We're going to be looking at initial rates. So here is my generic rate law. I have my K in front. I'm going to raise my oxygen to the N and my nitrogen to the M. Remember, K, N, and M must be determined experimentally. They do not come from the balanced chemical equation. So I need some experimental data. Okay, here we go. I've got 3 different experiments. I'm going to use all this data to determine what I need to determine. So starting with oxygen, just like before, I need to choose experiments where my data for oxygen is changing, but my data for nitrogen is staying constant. So I'm going to look at comparing experiment 1 and experiment 2. My oxygen concentration is changing, but you can see my nitrogen here is staying constant. All right, so here are the rates I need. Let's set up my proportionality. Okay, comparing rate 1 over rate 2. Again, making sure your concentrations of oxygen are going to be 1 over 2, and all of this is raised to the n. Okay, I'm just simply plugging everything in. So I'm going to put 707 over 500, and here are my concentrations for rate 1 and rate 2. Again, this is raised to the n. So let's simplify these expressions. So I get 1.414 is equal to 2 to the n. Now this is not so obvious what the value of n is, at least not to me. Maybe it is very obvious to you. So what do you do when you have a situation like this where n is not obviously either 1 or 2 or even 3? Well, you can use logs to help you. So I'm going to take the log of both sides. So here we go. I'm taking the log of both sides of the equation. When I take the log of both sides of the equation, it means I can pull this n down out of the exponent and put it in front. So here now is my expression. You'll notice n is down here. It's in front of my log 2. Now I can solve this very easily, and I get n equals 1/2. If you're ever unsure if your value of n is correct or not, if you've gone through these steps properly, just plug n in back in this expression. What is 2 raised to the 1/2, or what is the square root of 2? You're going to get 1.414. So it's always nice that you can do these internal checks to make sure your math is done correctly. My value of n is 1/2. That means the order of my oxygen is 1/2. We're going to do the same thing. Now let's do it for nitrogen. Okay, so let me clear out all my marks on my data table and start clean. Okay, so if I'm going to determine M for my nitrogen, I need to choose experiments where nitrogen is changing but oxygen is staying the same. So I am going to compare experiment 2 and experiment 3. You can see my oxygen is staying the same, my nitrogen is changing. Okay, so these are the rates I need. Let's set up my equation. Okay, so I'm going to compare rate 2 to rate 3, making sure my concentration of nitrogen is 2 over 3 as well. And of course, this is raised to the m. Let's just plug numbers in. All right, so this is just going to be 500 over 125, and my concentrations are going to be 0.04 over 0.01. Again, let's simplify these fractions, and we get 4 equals 4 to the m. Again, this is a really obvious one. M equals 1. 1 is the order for our nitrogen, and I should write over here 1/2 is the order of our oxygen, and of course our overall order is simply the addition of n plus m, which is 1/2 plus 1, or 1.5, or you could also call this 3/2 if you want. All right, so our last step is to determine our value of K. So I'm going to rewrite my rate law with my values of N and M plugged in. Here we go right here. I can use any experiment to determine my value of K, but I'm going to use my data from experiment 1. So let me clear off my marks and let's use experiment 1. All right, here's all my data for experiment 1. Now it's time to plug our numbers in. Okay, so here we have our rate. Again, we don't know K. We have our concentration of oxygen, our concentration of nitrogen. Again, don't forget this 1/2. All we have to do now is plug it into our calculator, solve for K, and we get a value of K of 1.2 times 10 to the 5th. Now that I know my value for K, I can write my complete rate law. And down here is my complete rate law. It's a little bit long this time. So I plug in my value for K. I make sure that I plug in for my value of N, and of course M is equal to 1. So this is my rate law. It takes a little time to get the hang of these, but once you practice a bit, I promise they will come more easily. I hope you found this video helpful, and thanks so much for watching.